Konnichiwa, my name is Asman Samasi and welcome back to day 5 of the 100 days of deep learning. In this video, we are going to take a look about the optimizer and the loss function. Okay, it is one of the important function in our deep learning. Okay, so in our previous video, we understand basically how to initialize a model. Okay, basically it's like initializing the brain of a child. Then now we are understanding the two things here. Okay, first is the loss, which basically tell the deep learning part that what actually loss it for our particular problem, and the optimizer tells basically how to update the way to correct the loss. Okay, so basically it's optimizer tells on how to minimize the loss. Now comes our loss function part. Okay, so as I already told, loss function basically tell what does bad even mean for our model. Okay, so basically imagine a child going to school and basically we are telling him that what actually bad means. Is it like scoring low in English, or like can't able to remember the numbers, or doing mischief? Okay, basically we are telling on what actually is considered bad. Okay, in our deep learning is basically the criteria for punishment. Okay, and how severe the punishment should be in our deep learning part. So basically in our loss function, it takes here two data set. One is the prediction and second is the target. Okay, so the loss function will compare between prediction and target and give a single scalar number. Okay, and this scalar number will tell basically how wrong the model is. Okay, and the whole training part is to minimize this number. Okay, this scalar number. So once again, let's see here the loss function tells basically what the criteria for punishment is. Okay, and how severe the punishment should be. It basically takes our prediction and target and give a scalar number, and that scalar number basically tell us on how wrong the model is, and the whole agenda of the training is to minimize this number. Now, what types of loss function are there? So since our pure deep learning or our pure machine learning have two main tasks. First is the regression and second is the classification. Okay, you must have known about both. Okay, first is the regression, where we are predicting and continuous value. Okay, so here we have three loss function. First is mean square error, then mean absolute error, then is Hilbert loss. Okay, so here in regression we are predicting and continuous value. Okay, and here the penalty is raised based on how far the value is from the predicted value. Okay, so here you will see the real value is 25, but here prediction is 3. Okay, so the difference is 2, so here it will be very small loss. Okay, here the difference is 3, so it will be a higher loss than the first value. Here you will see that the value is very far away, so here the loss will be very high, and here in finally here the loss is maximum. Okay, the difference is 80, so here the loss will be very high. Okay, the whole training module is to minimize this loss. Okay, and it is done by using three functions here. Okay, so let's dive into it. So first is our mean square error. Okay, so basically it squares the error between this. Okay, so for example here, if it's here 2 difference, it will square it to 4. Okay, our mean square error. And here it will be 9, and here 33 square. So here you could see that it's very high loss here, and here it will be maximum loss. Okay, square here, it basically square the distance between them. So here we technically penalize the very high predictive value. Okay, here the pros is that here basically we get very smooth graph. Okay, so here the loss will be very smooth here. Okay, for our each values. Second is that it penalize large errors heavily. Okay, so you could see here that after here the error distance becomes in 2 digit, it penalize it very heavily. Okay, and for small numbers it penalize low. Okay, here cons is basically it is very sensitive to outlier. Okay, so here if here the 100 was an outlier actually, so here it raises very high error without any real action. Okay, basically it's useless to raise this much high error if this 100 was actually an outlier here. Okay, so it's basically used when regression or Gaussian noise assumption. Okay, basically we generally or most famously use this loss. Okay, mean square error loss for our regression tasks. Mean absolute error is the absolute error between these. Okay, so here basically we measure the distance between these. Here this one is all about mean absolute error. Okay, here the pros is that it very robust to outliers. Okay, so even if 100 is an outlier, it is doing a small error here. Okay, it's not like heavily penalizing it here. Okay, like this here, and it is very sparse gradients. Okay, so here is some value become to 0. Okay, in our mean absolute error. Cons is that here it's not smooth to 0. Okay, here the graph, if you will make, it will be not smooth enough. Okay, and second is that it is very slow to converge than our MSME loss. Okay, it's useful in our noisy data or where the outliers matters less. Okay, so here if there is an outlier here, you will generally use mean absolute error. Then finally we have our Hilbert loss here, which is defined by NN dot smooth L1 loss. Okay, here it's basically merging the two techniques of our MSME and mean absolute error. Okay, so for small value it acts as our MSME, and for large value it acts as an mean absolute error. Okay, it have very stable gradients and it is very widely used in our detection. Okay, like our YOLO, you only look once, and our RCCN. Okay, is very widely used in our deep learning regression problem, and we generally use our Hilbert loss only. Okay, next to our MSME loss. Now going to our classification. Okay, Also here one thing you must remember that if it's an if the loss is here regression, okay, it the layers, okay, of our model class would always end it with a linear layer only, okay. So here the model will only end with our linear layer, okay, nn dot linear in our final layer of our model class, okay. In our classification we have two types of classification, okay. First is the binary classification and second is our multi-class classification, okay. In binary classification the choice is about dog, cat, 0, 1, true, false, okay. This is called binary classification. So here in our binary classification we could use two error here, okay. First is the binary cross entropy and second is the binary cross entropy with logits, okay. Here the code is this, okay. So here binary cross entropy we use the probabilistic interpretation, okay. We will get like 0.7 for our dog or for our cat we get 0.3, okay. So here we get our probabilistic nature, okay. So here the whole output will become our like 0.3. We then choose to have our threshold for our binary class. If it is more than like 0.5 we get as dog, or if it is less than 0.5 we get the cat, okay. So here in our binary cross entropy we have our threshold, and here the threshold defined the the output will be dog or cat or our true or false, okay. So here we get probabilistic interpretation, okay, like our 0.3, 0.7 etc, okay. Here and here you need to understand that each neural network should end with sigmoid layer only, okay. This one, it's also numerically unstable if you used incorrectly, okay. So it's generally not used in our binary classification, but our binary cross entropy with logits lost is used, okay, mainly in our binary classification, okay. It is defined using this, and the pros is that it is very numerically stable, it is very faster, and it is a very correct gradient, okay. And also for this you don't need to end out your neural network with like sigmoid, linear or etc, okay. Anything is fine, and here the binary cross entropy logits lot with logits lot will output in our logits only, okay. So for example, if you have your dog and cat, it will give us each thing probability, okay, like our logits here, and we then define our final loss here. Also here the loss is calculated and defined by how confident the model is wrong, okay. Confident wrong. So for example, here the real value is cat, but here the deep learning predict is a dog, okay, with an confidence of 0.8, okay. So here it will give a very high loss here, okay, since the model is predicting wrong with very high confidence, okay. So here it will raise error here, okay. Second is that if it is predicting dog and the real value is dog only, but it is predicting with 0.3, okay. I mean the value is correct, but the confidence is very low, then also it will raise very high error, okay. Since we need here confidence with our correct answer, okay. And finally in our cat it is predicting the real thing with our confidence of 0.7, okay. This is right, and it will raise a very low error here, okay, in our cat. So in our classification problem, we penalize on how confident the model is wrong, okay. For our multi-class classification, we have our cross entropy loss, okay, which is defined by nn dot cross entropy loss. For our multi-class classification, here the pros is that it is very industry standard, it is very stable, it is very efficient, and the cons is that it expect class indices, okay, not one hot encoding. So here the dog cat or our cow will be sent as our 0, 1, 2, okay, as an indices here, not our one hot encoding, okay. Like you can just number it anything, okay. Like here if the cat, dog and cow is like 0, 1, 2, so you can number it like 2, 1, 0, okay. Here the basically the class indices matter, okay. And here also you don't need and to end your neural network with a fixed layer, okay. For our binary class with our cross entropy, we end our neural network with our sigmoid layer, and for regression we always end with our linear, okay. This thing you must memorize it now, okay. Now coming to the optimizer function, okay. So basically here the optimizer function tells on how to update to minimize the loss, okay. So here the child did an error and the optimizer function will tell on how to improve it so you don't get that error next time, okay. Here the optimizer updates value using this formula, okay. 0 t plus 1, which is our next value, is equals to our previous value minus update, okay. So this is how we update our parameter, okay, and it is based on our gradients, learning rate or our momentum, okay. Now what are the types of optimizer function, okay. So we have here 5 optimizer function depend on our basic or our adaptive, okay. So first is our SGD, okay, but before understanding it, you must understand that why are we focused on gradient, okay. So here basically our optimizer function is basically trying to lowering the gradient, okay. So as you know, in our machine learning, deep learning, it's about the optimizer problem, okay. So here we need to get in the lowest loss possible, okay, and we get this using our optimizer function only. So here, like, if we started training from here, we need to get the lowest possible loss value here. Okay, so here this is the lowest possible loss value, and that thing we want in our optimizer function. Okay, in our machine learning, it is all about minimizing this loss. Okay, that accumulates in our gradient. Okay, so here in our gradient we actually get the lowest loss possible. Okay, the gradient only tells where to move to lower the loss. Okay, and here the gradient is the direction of the steepest hill. So basically, if we calculate gradient here, it will tell us on which direction to move to get higher loss. Okay, but here we walk downhill here. Okay, we basically walk in the opposite direction to get our optimal solution. Okay, and once we get the minima here, we could say that our deep learning get the optimal solution and it is ready for the deployment. Okay, now what are the parameters? Okay, so we could define parameters as the learnable numbers inside a model. Okay, so here for now, just keep in mind that each neuron in our model class is an parameter. Okay, so here one neuron actually work as a dial here. Okay, as a knob that we could turn on and off. Okay, with our weight. So here for one neuron we have our one weight. For 4 neuron we have 4 knob, and for our real case scenario, if we have 4 hidden layer with our 10 neurons each, okay, we have 40 dials for our that problem. Okay, and the whole deep learnings works by, I mean, revolving that dial. Okay, so if this knob is basically gathering more loss here, we gave it less weight. Okay, and if this knob is causing us very less loss, then we will give it more weight. Okay, so finally our basically deep learning works by, if an layer is causing very high loss, we give it a lower weight so that it don't cause that high loss, and if an model parameter is giving us very less loss, we will give more weight to it so that we can extract meaning. Okay, and we will go towards the optimal solution. Okay, so basically finally the optimal solution finally depends on a particular dial weights. Okay, for each parameters, and in our deep learning, our job, the optimizer job is to find that dial weight to minimize that loss. Okay, now coming to the learning rate. Okay, so basically what is our learning rate? So basically it is the step size during our updation. Okay, so here this is our loss curve. Okay, so here the learning rate will tell the optimizer on how fast we should update, so we go towards the minima. Okay, so if the learning rate is too small, okay, we will take very small steps here, and so here the learning will also be very slow. Okay, in contrast, if we have a very high learning rate, okay, we will take very high step size, and in most of the cases it overshoot or explode, okay, or basically do here zigzag motion, okay. So here the learning rate, the parameter and gradient is defined. So let's now understand the types of the optimizer function, okay. First is our SGD function. Here it is defined by TOS dot optimum dot SGD, okay, and then you pass the model parameters, basically the dials that had to be updated, and here the learning rate to specify on how fast we should update the weight for and loss, okay. Here the SGD is very simple, have a very strong generalization, and is very memory efficient, okay. But here the cons is that it has very small convergence, okay, and it is very sensitive to our learning rate, and it is used mainly in our research or large vision model, okay. So basically SGD whole idea is simple, is that we get loss here and we will move towards the learning rate with equal step size, okay. We will not change our step size and we will be going towards the minima, okay. Now we have here is the SGD plus momentum, okay. So here when we add here momentum equals to 0.9, it basically tells on how fast we should roll towards our minima, okay. So it will be very faster and it will have very less oscillation than our SGD, okay. But here the momentum needs to be fine tuning, okay. So it basically adds an inertia towards our minima, okay. If the loss is good, it will add an higher momentum, and in that way we will get very fast our minima, okay. Then we have our RMS propagation. Here it is defined in the same way with the TOS dot or optimum dot, but here the RMS propagation is passed with our model parameters and our learning rate, okay. Here the learning rate should be small, okay. Here in our RMS propagation and our ADAM. In our RMS propagation, we used our moving average of square gradients to normalize parameter updates, okay. So instead of going with our velocity, we change our learning rate depending on we are going towards the minima or not, okay. If we are going towards the minima, we increase our learning rate, okay. So we could go towards the minima fast, and if the gradient is changing very slightly here, so the learning rate will be slow here, so that it converges to a minima here, okay. It is good for our RNNs, our LSTM and our GRU, and it handles varying gradients, okay. So here in our varying gradients, here the learning rate, here our RMS propagation optimizer is very useful. Also it can convert to sub optimal minima, okay. So here if you will see that here the suboptimal minima is here, and if your RMS propagation you are using, then here the chances of stucking in the sub optimal minima is very high, okay. Now we have here ADAM, okay. this one is the most widely and recommend to use, okay? Adam function. It is defined using the same way, just that you pass here Adam, the model parameters and the learning rate. Okay, here it have your faster convergence. Here also you need minimal tuning, and it should be your default choice, okay, for your any deep learning problem, okay? But here it could be worse than our SGD, okay? And it could sometimes overfit, okay? So that thing you also should take care, okay? Here basically the Adams tracks your velocity and magnitude, okay? And basically it update, and basically here each parameters, okay, here in model.parameters are given its own learning rate, okay, in our Adam. Here we basically change learning rate for our depend on your curve, but here in Adam we get our learning rate for our each model parameters, okay? In our Adam W, it is mainly used for our transformer, okay? Transformer is defined the same way, just that here the learning rate is very small, okay? As the transformers are basically high weight models, so we need here very less learning rate so that we converge very slowly to our optimal solution, okay? This is mainly because the transformer have very much model parameters, okay? And if you use like very high learning rate, then it will explode very fast, okay? Here it is used for better generalization, and it is used mainly in our transformer, okay? It is slightly slower than Adam, but if you are using transformer, then this is the required optimizer, okay? It adds a proper weight decay, and it keeps learning rate so slow so that the model don't explode, okay? So this was all about our loss function and our optimizer function, okay? So the final conclusion is that for our regression we always use our Haber loss. For our binary class we use our BC with logis loss. For our multi-class classification we use our cross entropy loss, and for our optimizer we always use Adam, okay? We could change this, but for our general tags we basically stick with our these functions, okay? So that's all for today, and meet you in the practice session. Bye bye.